All right, this is the reaction of benzaldehyde to make benzoin using thiamine hydrochloride, right? This is a very popular reaction. It used to be done simply putting benzaldehyde, mixing it with cyanide ion. That worked really good. They came up with this alternative method using thiamine hydrochloride, right? So the way this reaction works is TLC. You might as well take a look at it right now. If you use 10 to 1, and I need a pointer here, which ran away from me. So this one I ran in 10 to 1. You can see how benzaldehyde, as you would expect, goes up here. Notice how that spot is small enough, and these two other spots, and they're nice straight lines, which is what you try to do. Pure benzoin in the reaction. So benzoin, because it's an alcohol, likes to stick to the gel, unlike benzaldehyde, which runs. If you were trying to get this to move faster, you could increase the polarity of the solvent. But anyway, in a lot of folks, like when I did mine, it was like 56% yield. It's often common when it works. So that's the reaction we're talking about. Let's just quickly go over what the spectra look like. Thiamine hydrochloride, this is what the UV looks like. This is an aromatic ring of sorts, even though it has two nitrogens in it. So this is the typical, and you could, as you'd expect, vigorous enough pi to pi star transition to get that typical peak at 250, a very large one. We just have to show it. Benzaldehyde, we've done this before. That's what the benzaldehyde peaks look like. This one should have had a number on it, but that's the benzaldehyde. Make sure you draw your structures on your spectra. The product looks like this. So really, what is the difference? We had a number on the first hump, 207. This first one is 207. So I mean, the product is strangely going to look very, very similar, right? Very similar, just like acetophenone. Now, some people could argue, when you look at this, typically the intensity of one peak versus the other, that normally stays even when you decrease the concentration, whereas the product, this one at 207, is more prominent than this one. So those heights typically stay in sync. And then we move on to IR. So benzaldehyde, we've done this before, but I will do this again. Whenever you see a little spike here for a carbonyl compound, when it's clear as day, a little tiny sharp spike, that's the overtone of the carbonyl C double bond O stretch. These just over 3,000 ones are sp2 hybridized carbons with an H on them, stretching. This is the classic 27 and 28 Fermi doublet for this hydrogen, stretching on that carbon. It's an aldehyde CH stretch, the classic Fermi doublet, right? The carbonyl C double bond O stretch is 1702. This collection of, even if you see it 1654 along with these two and even that, you can circle those. C double bond C aromatic ring stretch. Mono substituted, you look for a 650-ish, or that's 650 is that one. You're looking at 688, which is that one, and the 745, those two, is the out of plane bending CH of a mono substituted aromatic ring. We often look down here because your Pavia book will show it. I would not circle this because it is not the clear 4 little peaks on descending order, so I would not bother circling that. I don't have the thiamine hydrochloride. If you have it as your IR, you can just have it in there for reference. You don't have to analyze that one because the IR for this one has so many strange looking stretches, plus it's a salt. You would expect to have a lot of strange looking stretches. You don't have to assign that one if you have an IR, but the product you do. So the CO stretch, this, even though I have a question mark, we'll do that in the discussion, but this is, even though it's two of them, is the OH stretch of the alcohol. And when you look closely here, you see just over 3,000 the C carbons that are sp2 hybridized with a hydrogen stretching. The one here make it 2 that are just under 3,000. That would belong to the H that is on that sp3 carbon stretching. Then we move on to the carbonyl 1678. It's that carbonyl C double bond O stretch. You get 2 aromatic rings, so obviously, as usual, right around 1600, this, and even this. Normally we circle it just like Pavia. Say aromatic ring stretch or carbon double bond carbon stretch. And then we look for any potential mono, and you can see how you've got a couple here. You can circle this and just say mono substituted aromatic rings out OOP bend. So that's IR. Now we move on to the proton. The interesting thing, this was run on our machine by someone in the past, Pretty. She had done that. So what I have here, first of all, that hydrogen, D, sometimes it will talk to the hydrogen there. Sometimes D and E positions are talking. If they are, you will see 2 doublets. The one at 6 belongs to D, the one that can move. This one can be found anywhere in here, but that one is the OH hydrogen. All that's left is aromatic, so let's do a count here. What we do know is the 2 H's labeled A and F. No. One of the things we know, let me take that back, the 2 H's at A, when they're close to an aromatic or a carbonyl right there, that normally puts A slightly to the left. So when you look here and you see this, which is in this case it looks like 2.2, looks like roughly 2 H's, that looks like a great candidate for A. The remainder, 7.7, but think of it, this is a little over 2. So if this is 2, so A is accounted for, what's left? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 H's left. So all the remaining aromatics add up very close to 8. So this makes sense. Call this A, call this all the rest of the aromatics, and we're good. When she ran hers, you can see that it looks very, very clean. Now, some of you, as I'll show you in a minute, if they're not talking with each other, and that happens, this one is a singlet, and this would be a lump. So I'm going to show you one that was run at the university on a 500 megahertz machine. So notice the aromatics. You had that and then a blob on ours. This will be much nicer looking on a high resolution one. So the one that we labeled A, see how it's a nice doublet? And then what's a giant forest for us is the rest, so we won't bother with it. As promised, the hydrogen D, which is a nice singlet right around 6. And then this one, see how they're not talking? This is not a doublet, and this integrates to 1. That one is the blob, that is that hydrogen. What else they had is a little bit of water on that day that they ran theirs. Now the corresponding carbon for this one run in the past as reference, probably on Blackboard. A lot of aromatics. Let's go after position F as I've labeled it. So it's got to be in the sp3 region. And when they ran it, see this triplet at 77, that's the solvent chloroform D, but right down here, right on the side, that right there is carbon F. Carbon E, the carbonyl, is this one way out here at 199-ish. And we notice that carbons that have no hydrogens on them, quaternary carbons are the shortest. So it stands to reason that D and G with no hydrogens on them should be 2 small ones. So notice how that's very short, and see how here I've circled these 2 short ones. So circle that, and you could say they are D/G. What's left is any of the hydrogens like A and J. See how there's only one? When you have something like B, there's 2 of them, so you get twice the height. So positions B, C, H, and I, they have twice of each other, so they're taller. Positions A and G are often mid-height, so this one has one there and here. So I could circle that and call it J in A, and then I could say all of the rest would be the rest of them. Two of them happen to overlap and get taller, but so I think that explains it. This is a from Sigma Aldrich example. You can see how it's a little cleaner. See how they have less chloroform, so that one peak is taller. That belong to that carbon. And you can see you get those two short carbons along with the carbonyl here. So it looks very much the same. That's your carbons. So now we'll move to discussion-based stuff. So what I could start with is the mechanism. So the mechanism is found online, okay? A lot of students just, now you don't have to know it for your test, but it makes sense to put it in your lab because you could just write it in your book from online. Now, how this is gonna look. I expect you to come up with at least something. So with a little bit of looking into this. So for instance, I found this one years ago. Somebody did a multi-synthesis, the exact one we're doing. And they even outlined talking about the thiamine. That's the website I used years ago. So you turn, and this abounds. There's many people who do this. So one of the places they're talking about the mechanism a little bit, the part of thiamine hydrochloride that they're talking about, they're talking about how basically with base or something else you can make a yelid, and that yelid, right, is what ends up reacting with. So when you guys add a little bit of base to your thiamine hydrochloride, part in the R is the rest of it, right? But you're making this what they're calling a yelid, right? It's a base, and it goes to attack what looks like aldehydic carbon. The H, I'm not sure where they're claiming that comes from, but they're saying the enamine, the yelid attacks it, forming what's called an intermediate enamine, as you remember from last semester what that means. So the enamine is that one. And it goes over to this. This is the official enamine right there. So that shows you how you're going to make a yelid that represents an intermediate in your reaction energy diagram. Then you go on to make the enamine, which is another intermediate before you get the final products. So when you make this reaction energy diagram, I don't expect anything that's great, but in conjunction with some of this information from this mechanism what's talked about, you can easily basically say things like, when you start off with your starting material and you add base to whatever, and it tells you to keep it cool while you're forming what they call a yelid or an intermediate you're going to use. So the very first step, whether you make the yelid or whatever it is, it's exothermic because you got to cool it. So somehow, some way, that first step will be exothermic. Then you take that yelid according to them, and you're going to react it with your aldehyde to make an enamine of some sort, right? And then it carries on to your final product, right? Now, whether the overall reaction, I'm pretty much thinking the overall reaction start to final finish is probably exothermic, only because of whatever's happening up front is quite warm. And second to that, the original prep used to say heat, and I'll point to it right now. One of the original preps we used to use was this. And you notice how it basically said you're going to add your benzaldehyde and then heat to 60 for about this time. But then when we read a little bit further, it says alternatively, the reaction mixture at that point, when you add it to the aldehyde, you can just let it sit for 48 hours in your locker. So obviously, it's a slower reaction. So you could arguably say that it might be this activation energy that just takes time to get over, and that's why heating it made it go faster. But even this last step really does seem like it's probably exothermic or very close to it. Right? It's not heavily exothermic and it's not heavily endothermic. So that's about all we can say as far as that is concerned, but it's interesting just to From an industry point of view, if you're having problems with something like this, you have to look at the mechanism and think about the conditions you could tweak to make it better. So the yield. A lot of times they have problems getting product. Now what they're going to say here is things like, says in this prep that you should use a brand new bottle of thiamine hydrochloride because they're thinking that it oxidizes. But yet at the same time, we've tried this. We had a TR project where they actually used brand new thiamine hydrochloride and 4-year-old one. And the last student to use the procedure we're using now found basically no real difference. So there's a bit of randomness to this. And even to this day, what you guys are using is the best, works the best so far, but there's always some randomness to it. Everybody could use the exact same thiamine chloride, exact same benzaldehyde, whether it's distilled or not, and it seems to make no difference. So we're still a little bit left out there. You might have to end up doing 5 a few times. But the one thing we know is whenever there was no crystals when you're done your reaction, they do an ether extraction, they basically only ever see this. And it's very rare to see any product whatsoever. So it's either absolute failure, right? Or you get crystals is typically what happens. The other thing I can comment on, and then we'll call it a day, is why in the infrared do you see 2 peaks? And basically it comes down to this. When you're running it in liquid form, this forms a 5-membered ring of sorts by coordination, and it can do it 2 different ways. So you normally get 2 different energy spacings, and that's why you see 2 absorptions for that. The OH stretch has 2 different ways of hydrogen bonding. So that's why it looks like that. That's all we got.